So first of all, I want to say it's a real pleasure to be here in Ottawa and see so many familiar faces and some not familiar faces. And I hope to tell you today about the research that I do in a talk called The Cosmic Gift of Neutron Stars. And, you know, you hear the word stars, and I think if you say that word to many people around, certainly youth, you might picture something like this. And that is not the kind of star that I'm talking about today. That's perhaps, you know, maybe that would be interesting to talk about too, I suppose. But this is something probably more like what you're expecting. This is a lovely image of the night sky, and you can see there are lots of individual stars, some gas lanes, all sorts of things. But that's also not what I'm going to talk to you about tonight, because these are ordinary stars, the kind of stars sort of like what the sun is. That's a big, shining, gaseous sphere, and we know of billions of those kinds of objects in our own galaxy, in the Milky Way galaxy, but this is not what I'm going to talk to you about. Instead, I'm talking to you about a kind of star that is in many ways much more exotic than something even like our own sun. They're called neutron stars. And this sort of sketch of a neutron star, this is not an actual photograph, this is a sketch of what we believe they look like, has a lot of different components. And let me break it down for you a little bit so it doesn't look too bizarre. But you can see the little star at the center. And the idea here is that it has an imaginary axis that here is depicted in green, about which that star rotates. These are rotating stars, but from a different axis, so not from the rotation axis, from a different axis, from a different direction, it's emitting beams of light. Beams of light. And what your eyes are probably drawn to most in this picture are these white lines that are supposed to be representing the magnetic field of these neutron stars. And as you heard earlier, these are highly magnetized objects. So really those lines aren't physically there. If you were to look at a neutron star, you wouldn't see those lines, but they're meant to depict the location of what we call the magnetosphere. And I'm mentioning this now because it's going to play a sure. I want to be sure that you draw your attention to it. But in any case, the point of these neutron stars, and I'll explain a little more later, is that they rotate and they have beams of light coming out in a different direction from the rotation axis. And you'll see what that means shortly. So, cosmic gifts. The title of the talk was Cosmic Gifts of Neutron Stars. What did I mean by that? So, neutron stars have amazed astronomers upon discovery and continue to amaze today. It's a gift that I think of as it's something that keeps on giving. It could have been a scientific footnote. They were discovered back in 1967, kind of by accident. But today, they continue to be studied by hundreds of astronomers worldwide. And they yield surprising and unexpected discoveries even today that inform us not just about neutron stars themselves, but about a wide range of topics in astrophysics and in fundamental physics. They're kind of like cosmic physics laboratories, and I think this is why we can think of them as a cosmic gift. And what I hope by the end of the talk to show you is that we can continue to expect new gifts and more surprises from these objects in the future. So let's start at the end. So what do I mean by that? Where do neutron stars come from? What kind of star? Where does a neutron star? How is it created? So to understand the answer to that question, we have to understand about the life cycles of stars, how they're born and how they die. And so this sort of sketch over here gives an overview of that process, very simplistic terms. We start over here in a nebula of gas, a stellar nebula. We call that a star formation region, where stars are formed from agglomerations of very dense gas. And you can think of the star formation as having two basic outcomes, at least from the point of view of stellar evolution, how stars evolve. You can think of it as really two different directions. One is where an average star, kind of like the sun, is formed. And that star has its own evolution, as I'll describe in a second. Or you can think of more massive stars. And by more massive, I mean something like 10 times and even much higher than 10 times the mass of our sun. Now, of course, there's a continuum of stellar masses. It's not really like it's bimodal, like there's two separate populations. Really, it's continuous. But for the purposes of stellar evolution, two categories are sufficient. Because the lower mass stars, like our sun, their evolution is very well understood. They will eventually expand into what we call a red giant phase. Their outer regions of their atmosphere will puff up, cool down, and become red. And eventually, those outer layers of the atmosphere get blown off, and you end up with what is perceived as or is observed as a planetary nebula, which is one of those crazy words in astronomy that, there's a lot of jargon in astronomy that actually has nothing to do with what's going on. So planetary nebula has nothing to do with planets. And you might think, how could they name it that? Because initially they thought that it had to do with planets. Today we know it has nothing to do with it. But you have the outer regions of the red giant star being blown off, and you see the hot core of the star left behind. And eventually all those outer regions of the star get left behind, and you end up with just the solid core of the star, and that we call a white dwarf. And our galaxy is filled with white dwarfs. And I guess I saw on the screen Gilles Fontaine. I don't know if Gilles Fontaine is here, but he's one of the world's experts at white dwarfs and won a CAP medal this year. But the neutron stars that I'm going to be talking about are resulting from the other branch, the branch where star formation leads to more massive stars, 10 times and upwards that amount, the mass of the sun. In that case, the stellar evolution is also quite well understood. The outer layers of the star will puff up and create a red supergiant star, which is even bigger than a red giant, which eventually undergoes an explosive end called a supernova. And what's going on there is that the nuclear fuel that's keeping that star puffed up, that's withstanding the crushing inward pull of gravity, that nuclear fuel eventually runs out in stars. And when that happens, there's two possible outcomes. When you have one of these supernova explosions, which can be very, very extremely bright, and I'm going to describe the outcome of a supernova shortly. You'll understand a little bit more what I mean when I say very bright. Two possible outcomes of supernova explosion. For the most massive stars, and exactly where that border lies is not 100% well understood. We're actually making a lot of inroads into that question. Somewhere around 20 or 30 times the mass of the sun, you end up with a black hole. These are, of course, you've heard of black holes. Black holes are when the core of that red supergiant star has collapsed essentially to oblivion, beyond which nothing, not even light, can escape. And those are fascinating objects. But intermediate mass stars, the ones that don't quite form black holes and don't go the route of the white dwarf, what's formed there is called a neutron star. And that's what I study, and that's what the topic of today's talk is, these neutron stars. So they form from supernova explosions of intermediate mass stars. Now, you might be sort of worried by all this, and you might say, the life cycle of this, so the sun, is it really going to puff up into a red giant? And by the way, when it will engulf certainly the inner solar system. But if you're worried about that, don't be too worried, because that process takes billions and billions of years, and we think the sun, this is, if you can see it, this is where the sun is in that process, somewhere not even quite halfway there. So, if you want new tires or something like that, go out and buy them. Don't worry too much about it. We're doing okay for the next few billion years. Now, when I say supernova explosion, so let me just break that down a little bit more for you, what a supernova is. So when we have that red supergiant star here, as I said, the way what a star represents is a balance, a delicate balance between gravity, which wants to pull all the matter inward, and gas pressure, which can withstand that. So very hot gas in the center, high temperatures, high pressures can withstand that, as long as there's something that can keep that gas hot. And that's nuclear fusion. That's the fusion of hydrogen atoms, and eventually helium, eventually higher mass nuclei. But eventually it runs out of that nuclear fuel. It can't continue that forever. And then at that point, gravity wins, and the core of the star implodes. So really, a supernova explosion represents first a core implosion, and particularly when you form a neutron star, as opposed to a black hole, you end up with a bounce off the surface of that proto-neutron star, off the surface of a neutron star that forms. You get a bounce that then sends the outer regions of the star careening into interstellar space. And you end up with a neutron star at the center, and this gaseous glowing, we call it a supernova remnant. It's gas that's expanding very rapidly, thousands of kilometers per second, and it's glowing extremely hot because of the energetics in this process. This is an example. So you saw this in the slides that were running before I got on the stage. This is an example of a real supernova remnant in our galaxy. This is the remnant of a supernova explosion that we know occurred in 1054 AD. And I don't say that we know that that occurred lightly. This was actually recorded in ancient astrologer notes. And I say astrologer very carefully because in the year 1054 AD, there were, especially in China, in Korea, and Japan, people believed that events that they observed in the heavens were prognostications for events on Earth. You win the war, the emperor would get sick if something passed by. And they had fantastic, detailed records of everything that went on in the heavens there. And we know that the supernova explosion that created what today looks like this, looks like the Crab Nebula, occurred on July 3rd or 4th of 1054 AD, and at the time was as bright as the full moon for about a month. There's no mistaking it. Today, when you look with an optical telescope, that is with a telescope the kind, when I say telescope that you're picturing, a big mirror and you can go up to it and actually look in. We don't do that anymore in astronomy, but that's what most people picture when you hear the word telescope. This is a picture of the Crab Nebula taken with a very, very bright telescope indeed. And the thing I should also point out is you might be wondering, you see all these little white dots here, and those are our stars. Those are ordinary solar-type stars that are either in front of the nebula or behind it, in the foreground or the background, totally unrelated to the nebula. Anytime you look up in the sky, there's so many stars around, there's just going to be some by fluke in the field of view. Now, you might also be wondering, these supernova explosions sound really spectacular. How come we haven't seen any lately? And actually, we're due. So we know, roughly speaking, from watching other galaxies, how often these supernova explosions go off. And we think it's on the order of once or twice per century. There were other supernova explosions that were witnessed in the 1600s. Kepler observed one, Tycho observed one. But if you're wondering, and we know the rate at which these should be happening, and we are really due. So, if it happened tomorrow, there's no astronomer today who would be surprised. And if you're wondering, do you know which star might go off? And of course, we don't really know, but we can guess. And if you're familiar with this constellation, does anybody recognize this constellation? Orion, absolutely, Orion. There's the three stars of Orion's belt, and the knife and the foot. That's the bright star Rigel. And this star up here is called Betelgeuse. And it is a red supergiant star, and it is one that some astronomers believe is very likely to undergo a supernova explosion anytime in the next 10,000, 100,000 years. And that sounds like a very long time, but in astronomy, that's a blink of an eye. That's the lifetimes of stars are hundreds of millions of years. Any time in the next 10,000, 100,000 years is nothing. But 10,000 years is the same as next week as far as an astrophysicist is concerned. And so this thing could go off, and we wouldn't be surprised. And I included this slide just to make all of us feel insignificant. This is Betelgeuse in comparison to the sun. You see this, when we call it a red supergiant, Some people feel, astrophysics terms, they're so not creative, There's a giant, there's a supergiant, then a supergiant. But it really is, it is a large object. There's no doubt about that. Now, coming back to the Crab Nebula, if you zoom in to the center of the Crab Nebula, you see something really amazing. And you're wondering, I've gotten a little off topic. Suddenly I'm talking about supernova explosions, but of course that's what creates neutron stars. And there's many supernova remnants in the sky. We see lots of them. They'll typically live for several thousands of years. But the Crab Nebula is really special. And it's special because inside the Crab Nebula there is a neutron star. And that neutron star is not just any neutron star. It has a wonderful property of being what we call a pulsar. And so what do I mean by pulsar? So this is now another image of the Crab Nebula. And by the way, you might be wondering, Crab Nebula, that thing, why do you call it the crab? It doesn't look like a crab. And you're right, it doesn't look like a crab with modern telescopes. But to the first astronomers that discovered it, in fact, it was Charles Messier, a famous French astronomer, was the first one to really observe it. In the sketch that he made of what he observed through his little optical telescope, his sketch kind of looked like a crab, and the name sort of stuck. But in any case, if you zoom in to the center of the Crab Nebula, you notice, yes, all these white dots, they're unrelated stars, but there's one that actually is intimately related to the Crab Nebula. If you zoom into that little rectangle over here, and then not only do you zoom into it, but you take photographs in rapid succession. You take very, very fast photographs, and that's what's going on here. This entire time sequence lasts 33 thousandths of 1 second, so 33 milliseconds. You see, and the time is going down, and then to the next column, down, down, down. And you see one star that's always on, and that's the boring, unrelated solar-type star. And the other star is turning on, and you can see it turning on and then turning off. There, it's gone. And then it's on, and then it's on again, and then it's off. And that is what we call, that is the pulsar. Pulsars pulsate. They come and they go. The sun is always on, thank goodness for us, but pulsars, in this type of neutron star, turns on and off. And this crab pulsar pulsates 30 times every second. So it's a little bit hard to wrap one's mind around that. And you might wonder, well, what's making it pulsate? Why is it pulsating? And I started to tell you a little bit about the structure of neutron stars at the start of the talk. When I say pulsar, you might picture something that's actually getting bigger and smaller and bigger and smaller. And there are stars that do that. There are lots of the stars in the sky that actually do grow and contract and seem to get fainter and brighter. But that's not what's going on in the neutron star case. In the neutron star case, it appears to be a pulsar by virtue of its rotation. So I started to tell you about this before. Imagine a vertical rotation axis at the star, and then a separate axis which is defined by its magnetic field. It is the magnetic axis that is misaligned with the rotation axis in the same way that the Earth's magnetic axis, the Earth has a magnetic field, which is really, really good for humanity because it blocks out a lot of nasty particles from the solar wind. But the Earth's magnetic field is misaligned. In fact, it's interesting. The Earth's magnetic field wanders around a lot. There's probably people in the audience here who know an awful lot about that. But here on the neutron star, the neutron star's magnetic field is the axis of that field is defined by those two cones, because from the magnetic poles there are beams of light, beams of radiation coming out. And so we see neutron stars because they are like little cosmic lighthouses where you see the rotation of the neutron, you see the one pulsation each time it rotates. And you're already thinking, I already know that some of you are imagining, oh, well, maybe sometimes you actually see both poles, and then you could be mistaken and think it's rotating twice as fast. And you're right. That could happen. But we think it's rare. And the other thing to recognize is that, as I'm going to explain to you shortly, these objects are really, really small. The diameter of a neutron star, typical diameter, is only about 20 kilometers, which at interstellar distances is not resolvable, cannot be seen by any telescope on Earth. There's no telescope powerful enough to actually let you see that kind of movie. Instead, all we ever detect are these pulsations, that is, the changing intensity of the light from the star going on and off and on and off. That's all we get to observe. And so now the Crab pulsar, I started with that one. It's actually a very special pulsar in many ways, a very special neutron star, because you can see it optically. And if you went with a modest telescope and looked through, you would actually see those pulses 30 times a second, except some people can't quite make out 30 times a second. You might just see it being constantly on, but some people would notice it flashing. But it's special in that it emits optical light, the sort of light that your eyes can actually see. Whereas most pulsars do not. They're incredibly faint optically. You cannot see them even with the most powerful telescopes, even with space-based, like Hubble Space Telescope, you can't. They're too faint. But they are ubiquitous radio emitters. So it's sort of confusing to think about stars producing radio waves, but it's the same radio waves stars produce that your cell phone uses or that television stations use. That's another form of light. It's just another type of light, a different wavelength of light. And for some quirk of nature that we don't fully yet understand, neutron stars produce tons of radio waves. And it has something to do with the rotation and the intense magnetic field and the way a changing magnetic field produces an electric field which can accelerate particles, which can then radiate synchrotron and relativistic emission. So I'm talking a little bit to the physicists now, sorry. But all you really need to know is that they produce lots and lots of radio waves. And so what we observe is the radio intensity as a function of time. And you see these pulses, and the separation between one pulse to another pulse, that's what we call the pulse period. That's how often they pulsate. And this down here is some actual data. This is, you can see the individual pulses. That's an incredibly bright pulsar. I dream of pulsars like that. The vast majority of pulsars are really faint. You cannot see individual pulses at all. You have to use sophisticated techniques to tease it out of the data. These data were actually taken with this telescope. This is a telescope, and that's not what you're usually picturing. You're picturing a mountaintop, somebody looking through a giant optical mirror. No, this is like a satellite dish, except you have to understand this is a 100-meter aperture. So 100 meters across. Down here, those are two buses. This is a large building. Just setting the scale here, this is a very a large telescope. So you wouldn't want that for your satellite dish. That would be overkill. But for radio sources and radio pulsars, you need a huge collecting area to collect enough radio waves to actually be able to detect them. This radio telescope is the Green Bank Telescope. It's located in West Virginia, and it's the largest steerable radio telescope in the world. Now here, again, this is another schematic of the pulsar, and this is just another picture to drive this home. Here's the neutron star, rotation axis, magnetic axis with the radiation coming out, and these regions of magnetic field lines here in green, that's the magnetosphere. And as I said, I'll come back to that later. Now you might wonder, how can a neutron star get to spin so fast? Now, first of all stars spin. All stars rotate. Your own sun rotates. You probably don't know this, but it does. Rotates about once every 29 days. And all stars are known to rotate. And so, why should a neutron star rotate 30 times per second? That seems crazy. But we know that this rotation can happen thanks to a physics principle called the conservation of angular momentum. And what that means is that once you have something that is rotating, if you change its configuration, in particular, if you collapse it, make it much smaller, angular momentum must be conserved, and that object will spin up much faster. So the progenitor star, the one before it went supernova, its spin gets amplified in the collapse that creates the supernova explosion that creates the neutron star. And a very good way to picture that sort of conservation of angular momentum and spin up is with this figure skater. So I'm about to show you a movie of a figure skater, and I have to say, I really tried hard to find a Canadian one. But I could not find a good Canadian spin movie. And so if any of you know of one, just email me the link. But this is American silver medalist Paul Wiley. And what you're going to see him do a spin where he gets himself spinning, and then he makes himself as large as he possibly can. So he does that by extending out his arms, extending out a leg, and if he could, he'd extend the other leg, but that would just end in disaster. So he keeps one leg firmly on the ice, and he gets himself spinning, and then slowly he will bring his leg in and his arm in to make himself smaller, and you're going to see how his spin is amplified. There he goes. He gets himself spinning. There he is with all his leg and his arms out, and he's slowly bringing them in. And watch how fast he's going. Looks like he's going to drill himself into the bottom of the arena. But that was very nice. So that's the illustration of the principle of conservation of angular momentum, and that's why we believe neutron stars, or the vast majority of neutron stars, spin as fast as they do. And you might wonder why I would put a picture of the Garden of Eden up there, and that's because he was showing an example of original spin. Yeah, sorry. I'm really sorry. Just can't resist. Okay, so a few basic neutron star facts. So I've told you about the spin, I've told you the magnetic field, I've told you the magnetic axis, the spin axis are misaligned, I told you the prodigious radio emitters. You've learned a lot already. But let me tell you a little bit more, because these objects really are quite exotic. So remember, they form from the collapse of massive stars. So neutron stars themselves have quite a bit of mass. A lot of the star gets blown off in the explosion, but neutron stars typically have about 40% more mass than the sun. And for a lot of people, I recognize that's not a very intuitive number. I understand. So here's something maybe you could, a little bit more intuitive. That's about 500,000 Earths. So I don't know if that helps you, but if you can imagine taking, it doesn't help you, I'm sorry. I should translate it into, I don't know what, but anyway, it's a lot of mass. If you took 500,000 planet Earths, all of that matter, and you crush it into, like I said, a sphere that has a radius of about 10 kilometers. So crush it into something that's the size of a city. And you realize then the density of that matter has to be incredibly high, so that if you went up to a neutron star, and I'm not recommending that, very dangerous, don't do that, but if you went up to a neutron star with a teaspoon and you scooped 1 teaspoon of that neutron star material, it would weigh 1 billion tons. Now that's very counterintuitive, very confusing. How could that be? We're used to, maybe if you took a teaspoon of uranium and that was a little heavy to lift, but this is not matter. This is not normal matter like we're used to. Normal matter is made of atoms, where you have the protons and neutrons in the nucleus and the electrons buzzing around. Most of normal matter is empty space, whereas in the neutron star, that collapse, that huge gravitational collapse that occurs in the supernova explosion, that takes all the space away. All of that atomic material has been crushed down. There's no more empty space here. In fact, most of the protons and electrons have combined to produce neutrons. Most of the content of the neutron star, not all, but most of the content of the neutron star are neutrons that are crushed together. You could think of a neutron star kind of like, a little bit like a giant nucleus. And that matter is extremely high. And we think in the centers of neutron stars, the matter can get even more dense than than in a nucleus, possibly even 10 times or more dense than inside an atomic nucleus. Now, so if that density, if that's not exotic enough for you, if you need more, they also rotate, as you know, very rapidly. The Crab pulsar rotates 30 times a second, but that's not nowhere near the fastest pulsar we know of. The fastest pulsar we know of rotates 716 times per second. And I love saying that number because that pulsar was discovered on supercomputers at McGill University by my then student Jason Hessels, who's now gone on to be a professional astronomer in Europe. But 716 times per second. And, so I meant to say this. Sorry, this is the island of Montreal. This is the size of a neutron star. This is a great picture that NASA made for us. And that's where McGill is probably. This is Ottawa. It's not there. I should have brought it to Ottawa. But anyway, so 716 times per second. That's 1.4 times the mass of the sun, crushed into the size of a city, rotating as fast as your household blender. You have to stop and think about that, as fast as your blender. And I do stop and think about that a lot. And sometimes I get, I like to stay up really late. And sometimes I, Google search. And I wonder, are we faster than the fastest blender? And in fact, so the fastest blender I could find on Google is the Vitamix 5000, the fastest blender on Earth. Apparently, it's really good for smoothies, but it maxes out at 625 rotations per second. So I'm very proud that we have beat the blenders. So I'm glad you're this physicist, because I once gave a talk and there were a lot of biologists, and I got real flack because apparently in biology labs there are centrifuges that go over 1 kilohertz. And so we haven't yet beat the biologists, but we're working on it. So the fastest pulsar, yes, as I said, it was discovered. There's Jason Hessel's back on this really old computer. I think this computer probably is about as fast as your iPhone today. But back in 2006, and we keep searching for pulsars. And we're really excited to find faster and faster pulsars. And I promise this is the only equation here. But let me just convey this to you. Why do we like to find fast pulsars? Well, first of all, you have to appreciate how fast you would be going if you were standing on the surface of one of these neutron stars. We call the fastest ones millisecond pulsars because they rotate with periods of about a millisecond. And so this is just a very quick calculation of how fast, what is the speed if you were standing at the surface of a millisecond pulsar. And so here's speed. This is the circumference, 2 pi r. I stuck in 10,000 meters there. That's 1,000 kilometers. And 2 pi r over the time that it takes to go around once. That's about 1.4 milliseconds for the fastest one. And if you work all that out, that's about 15% of the speed of light. 15% of the speed of light. So this was velocity. There's a term for this. It's called very fast. And you might wonder about that number, because Einstein told us that nothing can travel faster than the speed of light. And we're getting awfully close to that cosmic speed limit with these millisecond pulsars. And so we are asking the very interesting question, how fast can a pulsar spin? And part of the research that my group and my colleagues, pulsar colleagues around the world, what we're doing is trying to answer this question. We're continually searching for faster and faster pulsars, not so much because we think that we are going to beat Einstein, that we're going to prove him wrong, but rather because of all the numbers here, the squishiest one, what I mean by that, the one that we know the least, is the radius. And so really, I put in 10 kilometers here. Could it be 13? Could it be 8? We don't really know exactly what that number is. And by finding faster and faster pulsars, we are constraining what the radius of these neutron stars actually is. And so why can okay, it's great. You could figure out what the radius is. And in fact, it's more complex than that, because we think long before the surface ever gets to be spinning close to the speed of light, the neutron star would probably break apart. If you spin something fast enough, it's going to shed matter. It's going to throw off matter. And so really what we're studying by finding faster and faster pulsars is exactly the nature of that ultra-dense matter at the center of the neutron star. So this is a picture, sort of a diagram showing you the structure, and it's quite a well-developed structure, mainly based on theory. It's sort of hard to constrain interiors of neutron stars, although there are some ways of doing it. But you see the giant question mark in the center. And I mentioned earlier, the densities are upwards 10 times nuclear density. At that stage, we don't know the nature of matter at those high densities. And that's one of the ways you can constrain it is by constraining the radius of the neutron star. And so that's one of the things we're hoping to do, learn about fundamental physics topic, the nature of matter at ultra-high densities using these celestial objects. Now, another telescope that I use, that my research group uses, is the Arecibo Telescope in Puerto Rico. This is the largest telescope in the world. The diameter here is 300 meters. So right here, this is a wonderful visitor center, 3-story visitor center. If you're ever in Puerto Rico, there's a fantastic science museum in there. And you can see this here is a catwalk. So you can go out on that catwalk, climb over here. You could fit, 100 people up there. This is a 85-foot. The way this reflector works is the radio waves come in, bounce off the surface, bounce into this dome here where there's There's something like an 85-foot telescope that's upside down that then bounces it onto an antenna, et cetera. This radio telescope, where we observe pulsars a lot, and we do a lot of our pulsar searching there, has been featured in some films. There's Jodie Foster, who starred in the movie Contact. And I'll just tell you a little story about that when they're studying, the beginning, if you watch the movie Contact, at the very beginning of the movie, they're staring at their computer screens at Arecibo, and they're looking, and they see, they were looking for aliens in that movie, and they see this beep, beep, beep go on, and they get very excited, and then somebody says, oh, no, it's just a pulsar. So I was particularly disappointed with that scene. But it also was featured in another movie. That's Pierce Brosnan, and I forget the other actor, but this was in James Bond GoldenEye. So James Bond movie featured the Arecibo Telescope, except they pretended it was in Cuba. It's not in Cuba. And that it was hidden from spies by water, that they filled it in with water, but of course this is actually a mesh. There's no way that you could fill it with water. But I will tell you one story here. There's a great scene where Pierce Brosnan is chasing the bad guy up the catwalk. And in fact, it wasn't Pierce Brosnan. It was his stunt double. And so he was too afraid to go on the catwalk. And so I've been on that catwalk many times. I'm very proud to say I've done things that James Bond was too afraid to do. Yeah, in fact, just to prove it to you so you don't think I'm lying, here I am. There I am, my hard hat, with my good friends, Maura McLaughlin from West Virginia University, Paul Ray from the Naval Research Lab, and we've climbed all the way to the top of that catwalk. That's at the very top of that. And if you look closely, yes, our knuckles are white. So back when we found the fastest pulsar yet, we published that in Science magazine. And at the time, Harvard professor Josh Grinley wrote a little article about our discovery, and it was called A Neutron Star in F sharp. So a neutron star in F sharp. And you might wonder, therefore, F sharp, what do neutron stars and pulsars have to do with music? And so now I'm going to tell you. So when you use a radio telescope, and we don't actually, you can do the following, even though we don't actually do it for research purposes, we do it for fun when we're bored. You can take the output of the radio telescope. It's an electric signal. You can amplify it. You can, digitize it and do all sorts of things to it. And then you can plug it into a speaker and you can listen to it. And so what I've brought here are some sounds, actual sounds of pulsars as recorded at radio telescopes. And I find this as a useful aid for showing people what these things are really like and how fast they're really rotating. So I'm going to now play for you the sounds of 3 different pulsars. So the first one, this is actually one of the brightest pulsars in the sky, pulsar 0329 plus 54. They're named for their coordinates in the sky. You hear those are the beats, the bursts of radio intensity being picked up by the antenna. In that case, they were separated by 700 milliseconds, or 0.7 seconds. The next one's a lot faster. This is a pulsar in the southern sky in the constellation of Vela. The period here is 89 milliseconds, or that's 11 beats per second, 11 rotations of the star per second. Where's my mouse? There. And so, right away when you hear that, you can do a little astronomy right on your own. You'll notice every now and again there's one pulse missing. But the next one always comes back exactly at the right time. So what's amazing about these objects is their rotation is very hard to jiggle around. They're incredibly stable clocks. So the different pulses might have different amplitudes. Sometimes they even skip one, but it's an incredibly stable clock. The next one will always come back right on time. The next one, 33 milliseconds. This is the Crab pulsar. My mouse doesn't want to. Why do you do that? No. Come back. Why? Hold on. Come back in there. Go back to view mode. Okay. So that's 33 milliseconds. And now it's starting to sound like kind of an annoying tone. It's not so, some of you can separate that into little individual beats. Some of you might just hear that as just sort of a nasty kind of sound. But that's 33 milliseconds. The last one, this is the second fastest pulsar known, 1.5 milliseconds, 642 times per second. And now the individual beats are so close together, and they're at a frequency that is similar to what you hear in the audio, to what sound waves do that you can hear. And so this sounds like an audio tone. So this is Pulsar 1937 plus 21, the second fastest pulsar known. And it sounds, and for those of you who are music aficionados, you hear some harmonic structure in there because it's not a perfect sine wave. It's actually a fairly narrow pulse. I'm going to skip this. Wait, sorry. Okay. Now, some pulsars, and we know, by the way, about how much time? 10 minutes. Some pulsars are really very lucky. They come with binary companions. That is, they're orbiting another star. That's a binary pulsar. And as I said, pulsars are excellent clocks. And this is really important. I want to drive this point home. This pulsar, 1937 plus 21, that's its pulse period. So that's the time of successive pulsations. And you can see all those digits. And the 3 in parentheses, that's the uncertainty on this number in the last digit. So not all pulsars are that fantastic clocks, but many of them are. And it's that clock-like property, particularly when you find them orbiting another star, that is incredibly useful for doing sensitive dynamical tests. And let me explain why. So how do we know when a pulsar is in a binary orbit? So there's a phenomenon called the Doppler Shift. Imagine you have a car traveling in this direction, it's blowing its horn. You have an observer over here, an observer over here. The observer who's standing in the direction the car is moving away from, it will hear a slightly different pitch of that horn. So if the horn to the driver who's sitting in the middle of the car sounds like this, observer number 1 will hear and observer number 2 will hear So it's a familiar train whistle effect. It's, of course, strongest if you're standing directly in the path of the vehicle, which I don't recommend. If you're off to the side and you hear the train coming, you hear like that. As it comes towards you, it's higher. As it moves away from you, it's lower. It's the same thing with pulsar. Oh, and this is what police use to find you when you're speeding. They bounce radio waves off the car and look at the change in frequency. So when you have 2 stars orbiting, one of them is moving towards you at any one time, and the other one's moving away from you. So you have towards you and away from you, towards you and away from you. The pulse period is Doppler shifted. Sometimes it's a little shorter when it's moving towards you, and sometimes a little longer when it's moving away from you. This pulse period changes, and because they're such fantastic clocks, we can measure that kind of change with extreme precision. So for example, this is a binary pulsar now. Now I've plotted the pulse period as a function of time, and these dots have error bars on them. So when we measure the pulse period, we can measure it very precisely, and you can see there's no question. It's obviously the pulse period is undergoing sinusoidal oscillations at a period of, in this case, probably a few hours. So some of these binary pulsars go around very, very fast. And in fact, the first binary pulsar was discovered in 1974 by Russell Hulse and Joe Taylor in a binary system where the pulsar was going around another star, we think it's another neutron star, every 8 hours. Now, every 8 hours, compare that, the Earth goes around the sun once every year. Here, these pulsars are orbiting each other every 8 hours. When that happens, classical dynamics, that is the dynamics, the motion that was discovered and studied by Isaac Newton way back in the 1700s, they break down very rapidly. And you absolutely have to use relativistic dynamics. And the best theory for relativistic motion is Albert Einstein's General Theory of Relativity, although, in this case, his theory was proven to some extent when he was alive in solar system experiments where the effect was quite weak. In binary pulsars, the effect is quite strong, and there's actually an interesting question, do relativistic dynamics work? Another aspect of Einstein's theory of general relativity is that as these objects orbit each other, there should be the whole reason that these objects produce gravity is that they distort the fabric of space-time around them. And so what that green grid is showing you is space-time. And in this case, space-time is undulating because of the motion of those objects. Mass in general relativity causes geometric distortions of space. And if the mass is moving, those geometric distortions get propagated outward. And that's called gravitational radiation, gravitational waves. So in Albert Einstein's theory, if you have something as massive as a neutron star going around some other star every 8 hours, there should be production of gravitational waves that takes away energy from that system. The gravitational wave takes some energy to distort space-time. That energy propagates outward, takes away energy from that orbit. And the pulsar orbit should decay, something that Isaac Newton would never predict. In Isaac Newton's world, in classical dynamics, the orbit should last forever. In relativity, in Einstein's theory of relativity, the orbit has to decay due to the emission of gravitational waves. And so when this pulsar was discovered, it was an interesting question. Was Einstein right? It became a new laboratory, a fantastic laboratory for studying general relativity. And you see here Hulse and Taylor, who discovered the first pulsar, they're smiling, they're laughing, and they're laughing because the pulsar, of course, Einstein could be wrong, but here is the data from years of observing the first binary pulsar, and what you can see here, so this goes from 1975 to, I think, 2005. These are data that are showing you something that is a proxy for the size of the orbit. If Isaac Newton's law was right, those data points should lie on this horizontal line where the orbit is unchanging. The line that you see here is the prediction from general relativity, and each of these data points has an error bar on it. It's so small you can't see it, but you see they lie perfectly along the general relativistic prediction. So this is one way that binary pulsars, and there's Joe Taylor getting his Nobel Prize in 1994. So, is general relativity right? Well, it's a cornerstone of modern science that demands testing. Albert Einstein may be a brilliant scientist, but scientists test theories. In his case, it passes weak tests with flying colors, and it has long been a question of whether general relativity would work in the strong field regime where GR really, really matters, but has not been well tested. Another example, how much time do I have left? 2 minutes, darn. Okay, I'm going to skip this one. You can ask me about the double pulsar later. Sorry. Oh, yeah. Okay. So just talking about neutron stars. Neutron stars, the gift that keep on giving. Pulsars, I just described, as in the Hulse-Taylor pulsar, they are sources of gravitational waves when they're found in binary systems. But these are a gift. Neutron stars can also be detectors of gravitational waves. So they can be both a source and an incredibly sensitive detector of gravitational waves because pulsar signals, they're perfect clocks, but if a gravitational wave passes between you and the pulsar, that changes the ticks of those clocks. That can affect the ticks of the clock in a way that can actually, we hope, be measured. And that, we're hoping, is the next gift from neutron stars. So an example of what can cause gravitational waves that pulsars can detect are, as I said here, merging supermassive black holes. So I have 2 minutes to explain this to you, so I might go a little over. But I really want to convey this to you. So if you look at any galaxy, including our own Milky Way galaxy, what you find, spiral arms, lots of stars, lots of gas. But at the center of our galaxy, and at the center, we believe, of every galaxy, of the billions of galaxies in the universe, there is what we call a supermassive black hole. And there's astronomy jargon, again, not being very creative. But what we mean by that is a black hole that is something like 1 million to 1 billion times the mass of the sun, a supermassive black hole. And so, here is an image of a galaxy. This is actually combined optical and radio image where you can see a beautiful dust lane. That's a galaxy. And you see these jets that are being spewed out. And the idea is that the black hole, the supermassive black hole at the center of this, we call it an active galaxy, can spew out these giant jets into intergalactic space. And that's, we think, is going on. At least there's a black hole. Sometimes it's active like this. Sometimes it's spewing out jets. Sometimes it's not. We think this is in every galaxy. Now, sometimes in the universe, there's so many billions of galaxies, sometimes galaxies collide. And in merging, sometimes you have galaxies that actually hit each other and merge. This is an optical image of two merging galaxies. It's called the mice. And you say, well, that looks like, how do you know those are merging galaxies? And that's because there are people who do computer simulations of what would happen if you took two galaxies of stars and gas, and you have to include some dark matter for those of you who know about that, and you merge them. And here's this computer simulation of two spiral galaxies that are merging, and you see if you just take a quick snapshot in that merger, it looks a lot like the mice. And that's how we know that the mice is two galaxies that are in the process of merging. But now if you look really closely at two galaxies, and here's another movie of two spiral galaxies moving, two spiral galaxies that are merging, and you zoom into the centers, each one has a supermassive black hole, okay? And when those supermassive black holes get really close to each other, they will orbit each other exactly the way binary neutron stars will orbit each other. You'll have two, instead of 1.4 solar mass objects, you have 2 billion solar mass objects there. And those will also produce gravitational waves. In this case, those gravitational waves conveniently get beamed directly to the Milky Way, which of course is nonsense. So they go throughout the universe, but in particular they go to the Milky Way. And here on Earth, with a really giant radio telescope, we can observe pulsars. And as those waves pass through the Milky Way galaxy, the time between pulses of these pulsars, and not any pulsar, some of them are too noisy to do this, you need the really precise ones, will get bigger and smaller, and that way we can detect the passage of gravitational waves. Now, you wouldn't want to rely on a single pulsar to do that. What if that pulsar was kind of crummy and you didn't know it? We need an array of pulsars in the whole sky, a pulsar timing array, and this is an experiment that we're doing right now. We're combining radio telescopes around the Earth. We're getting them to monitor a few dozen pulsars on for months and, in fact, for years. And we're hoping to combine the data from all of these sources and be able to look for correlated signals between pulsars that would allow us to detect gravitational waves from supermassive black holes. And we're hoping that this will be the next neutron star gift. So we started at the end. We're going to end at the beginning. Cosmic gift from pulsars. You got to hear pulsar sounds. We get perfect clocks in interstellar space. We get binary pulsars that let us test general relativity. I had to skip the double pulsar, but another gift we hope is soon to come. The next gift would be direct detection of gravitational waves from supermassive black holes using pulsars. And so with that, I will end, and thank you very much for your attention. And just also, I want to point out the fantastic group of students and postdocs at McGill University that makes all of this research possible, and also the various funding agencies that fund my research. And I thank them, and I thank all of you and the CAP for this great honor to be able to speak to you tonight.